Meet Dave. Dave is an accountant at a car rental company. The rental company owns 16 cars. When cars are new, their maintenance costs are low. But when cars get older, repair costs start to increase. Dave wants to know the car maintenance costs depending on the age of the car and gets an overview of the repair costs from the computer. Dave gets a report from last year and looks at the data. There seems to be a relationship between the age of the car and the costs. Dave plots the data in a diagram. The diagram shows a linear relationship between the age and the maintenance costs. Roughly, maintenance costs start at $200 and increase with $250 each year. If Dave wants to predict the maintenance costs of arbitrary cars, he needs to find the regression line. As we have learned, finding the function for this line can be done with linear regression. Let's start by defining the data points. We are going to reuse 90% of the previous code, but I'm going to start from scratch to repeat all the steps we have done so far. Let me create a new Python file called cars.py. I define a weight, bias, epochs, and learning rate. I chose the values arbitrarily and will adjust them when needed. I create the predict function. And finally, the training loop. First, I make the predictions for all training samples. Then calculate and print the cost. Now the backpropagation starts. I calculate the derivatives of the errors. From the error derivatives, I calculate the weight and bias deltas with respect to their inputs. I'd like to repeat that the weight deltas are calculated from the error derivatives with respect to the inputs. And bias deltas are calculated from the error derivatives with respect to the bias input, which is 1. Finally, the weight and bias are updated. Let me execute the code. Look at the cost. It is still decreasing at the end. I'll increase the learning rate. That was too much because the cost is out of control now. Let me try again. This looks better. I'll double the epochs. Notice that the cost is not nearing zero. But what does that tell us? Nothing really. More interesting is to see how the cost evolves. At the end, you see that the cost does not change much. That means that the network cannot improve much even if we train it more. So why don't we take the weight and bias and plot a regression line to see how we are doing? I take the weight and bias from the output and plot a regression line with them. Wow! Look at the regression line. It looks like a good fit. This shows that linear regression also works well even if the points are not exactly on the line. It looks like we don't need to adjust the parameters any further. So when Dave's boss asks how much a 4-year-old car costs, Dave uses his neural network like this. A 4-year-old car costs about $1,600 in maintenance. Is that accurate? Let's check it. 4 years is about $1,600. Well done, Dave. Before I started looking into artificial intelligence, deep learning and neural networks, I thought there was a lot of black magic involved. But as it turns out, a neural network is just a function. Granted, it is a function with a lot of parameters, but nonetheless, it is a function that needs to be trained. Speaking of training, using pre-existing data to train the network is called supervised learning. I have a question. Did you notice the 3-year-old car that had low maintenance costs? What happened there? Why is this point a bit of an anomaly? You'll see that in the next part where we add another input to the neuron.